suppose I have some data which is not linearly separable, right. So that is the problem that we have with perceptrons, right. So what happens if the data is not linearly separable? Perceptrons do not converge. So can we tweak our objective function that we have here to make sure that we can handle non-linearly separable data? Is that the right way of saying it? Is it okay to say non-linearly separable data was my question. Yeah, linearly inseparable data, right. So you have to be careful where you put the not, the negation there, right. So what we do in this case, yeah, somebody had a suggestion?
We can minimize some of the, we can associate an L function and minimize that.
Yeah, so how will you do this, right. So there are many ways, there are many choices you can make, right. Let me not play around with it. There are many choices you could make, but there is one particular choice which is seems to yield a very nice optimization formulation, okay. So what is the choice? I am going to say that I would really like to maximize the margin, right, and I would like to get as many data points correct as possible, right. So if you think about it, so there are a couple of things. If this is the margin that I want, right. So what are the problems here? Well, these data points are within the margin, right. So I have some data points that are within the margin, so I like to minimize such cases. There are some data points that are within the margin and erroneous, right. I would like to minimize such cases as well, right. If you think about it, if I try to get this correct, right, there is a gap here and there seems to be a gap here between the points. If I try to get this correct and moved my classification surface below, then the margin would have been reduced even further, right. So it's okay to get this wrong, but then what about this guy? Is he within the margin or outside the margin? Huh? Within, right. So the margin for that class is defined on the other side, right. So the margin for that class is this side. So anything to this side and x is within the margin. Does it make sense? Right? This will be yi times this, right? So this will actually be negative. So it is within the margin. Right? We want things to be greater than 1. Yi times f of x, we want it to be greater than 1, right? Greater than or equal to 1. This is going to be negative. So obviously this is within the margin. Right? Make sense? Right, so essentially what I want to do is minimize these distances. So you can see the distances I have marked here. So these distances I would like to minimize. Does that make sense? Right? So this is a certain small distance inside the margin, right? This is a large distance inside the margin. This is a very large distance inside the margin. And likewise, I can mark each one of these, and I want to minimize these. So let us denote them as xi1 to xi5, and I want to minimize those, right, essentially. So if I minimize the sum of these deviations I make along with my original objective function, right, I can handle. Why don't I minimize the minimum here again? That would minimize the maximum would essentially mean that I will try to get as many things correct as possible. So in this case I do not mind getting something wrong as long as the overall deviation is not, does not exceed a certain limit. See that the difference between minimizing the maximum and minimizing a sum is that I might as well give all of the sum to a single data point, it might be something that is very hard to classify, right? I might have one single outlier somewhere here, right? Let's draw. So this data might be perfectly separable, and I might have an outlier there. Okay. So now if I just say okay, minimize the sum of the things, it's fine, right? But if I say minimize the max, okay, then it's going to actually give me a hyperplane somewhere there. Okay. But like I said, many different formulations are possible. This one actually yields a very nice computation. That's one of the reasons people use this. Okay. So what I am going to do is, let me write it here. Right. So I am going to say that this has to be that we had already, right? I am going to introduce a slack variable. Okay. So it does not have to be greater than m, it can be some fraction lesser also, right? M is what I would really like, okay, but I allow it to have a slack, right? Ideally I would want most of these zeta is to be xi is to be 0, right? Ideally I would like most of the xi is to be 0. If I force all xi is to be 0, I am back here, right? But I really like some leeway, right? So I am allowing myself that leeway by introducing this xi is here. Okay, this is a very standard technique for relaxing constraints in optimization, right? That's one of the reasons people adopt this, right? It's a standard constraint. So another thing which I could have chosen is that, right? In fact, this is a little bit more common constraint, but it turns out that in this particular case, if I choose m minus xi instead of m into 1 minus xi, I end up getting a non-convex optimization problem. Okay. So we don't want that, right? So we actually end up doing this. So I drew this figure first because I wanted to get an idea of what these slack variables actually mean, right? So these slack variables essentially tell you by what fraction, right, you are violating the margin, right? So xi1 is essentially what fraction of distance you are coming in here from the margin. Like xi2 is what fraction of the distance you are coming in from the margin. So if the margin is m, so I have moved some fraction of the distance inside, right? So essentially that's what the xi tells me, right? So what are the constraints we have? That's your question, right? So the first constraint I have is, okay, all xi's have to be greater than or equal to 0, right? I don't care about points going to that side of the margin, right? So all xi's are greater than or equal to 0. And the second thing is whatever we have been talking about, right? I don't want the xi's to be very large, taken in total. So I want to upper bound them by a constant.
So why do all the xi's have to be positive?
So because I am talking about going that side of the margin, right? So if my xi's are negative, so essentially I will be imposing a tighter constraint than what I was looking for. So this will be like, it will be larger than m, right? This is, I will be having a thing that's larger than m on the right hand side.
Xi just represents the distance of a point to the line, right?
I'm sorry?
The xi just represents the distance of some.
No, that's what, it's a relative distance, right? So essentially this becomes what? M minus m xi, right? So originally it should be m, so it is now m xi away from there. Okay, so xi is essentially a relative distance, right, and if I make xi is negative, so this will become plus. So that will essentially mean that not only do I want the data points to be away than m, I actually am asking it to be farther away than that. So it just imposes a tighter constraint. So I don't want that to happen. Right. So and here we are essentially giving it a budget, right? We don't want it to be greater than the budget, right? Fine. So we saw such an constraint earlier. Where did we see such a constraint earlier? Where we had a budget. We didn't want it to be greater than a budget. Huh? So yeah, in ridge regression and lasso and other things, we had this thing, right? So wherever we are looking at this regularized regression, so we had this greater than a or lesser than a constant. And what did we do in those cases? We pushed it into the objective function, right? And then added a multiplier there. And then we said, okay, it has to be, right. So then there is a relationship between this constant and the multiplier that we put in the objective function, right. So likewise we will do the same thing here. I will do all the other transformations that we need to do, right, to normalize beta and things like that. So I will essentially end up with the same objective function I had there. Right. What? Greater than or equal to? Because we have gotten rid of the m, right? Why? How did we get rid of the m? M is 1 by beta, right? So 1 by norm beta, so we got rid of that. So anything else we need here? Right. So now that we have this objective function, what should be the value of C if I want a linearly separable case? If I want to solve the linearly separable problem, right, or I want to ensure that all i's are 0, what should the value of C be? This is just a simple question. Huh? Infinity, right? C should be infinity. So the larger the value of C, the more you are penalizing the violations, right? So the smaller the i's should be, right? So the larger the value of C, the smaller the i's should be, right? So this is a trade-off. So the larger you make C, the smaller will the margin be, but more you will be getting more of the training data correct, right? So if you, for large values of C, you are allowing a little bit more leeway in. Does it make sense? So if C is very large, C is small, then you are allowing a lot more errors to happen. If C is very large, then you are forcing the classifier to classify as much of the training data as correct as possible. Okay. The data is truly linearly separable and you make C very large, what will happen? You will find the correct linear separator, right? But if the data is truly linearly separable but you keep C small, what might happen? You might trade off errors in the training data for a larger margin, even if the data is linearly separable. Is that a desirable thing? Huh?
Sometimes.
When?
Noisy data.
Exactly. So if the data is noisy such that there are some data points that are closer to the margin, right, maybe 1 or 2 data points that are closer to the margin. So if you are trying to find the perfect linear separation, you will pay attention to them as well, right, and therefore you will end up having a low margin, right. But then if you are willing to ignore a few noisy data points, right, even if the training data looks perfectly separable, right, you might end up making a few errors on it, but you will get a more robust classifier, right. So can people visualize a situation? I am going to try and do something here, let us see if that works. Data looks perfectly separable, right, there is noise, right, is it still separable? Yes, right. That is more or less linear. See, the data points are point, okay, there you go, okay, there, it is still separable, right. If you try to solve it as a perfectly separable problem, that is the separator that you are going to get. But if you allow errors, right, so that will probably be the separating hyperplane you get, and that is probably a more appropriate hyperplane, right. Apart from being robust, it's also correct in an expected sense. So far no questions. Now we will move on to the whole the primal rule. So I just wanted to leave this on board till I wrote this down so that you can compare it, right. So it's all good. Okay, fine. Right, is that fine? So that is the primal. Oh, sorry. I mean, you have alpha, right? The xi alpha mu has to be greater than equal to 0. Yeah. I don't have to do that. Huh? What's that? Why is it?
Why do we have mu I? Why don't we just have one mu? It's a single condition, right?
What is the single condition?
Sigma psi I is less than equal to constant.
It's not a single condition. It's there for each I.
What about sigma psi I less than or equal to constant?
Oh, we need the sigma phi I less than or equal to constant. Do we? No, we don't, right? So that is why we put that into the optimization objective function itself, right? So by minimizing this, right, we are ensuring that sigma psi I will be less than some limit, right? And like I was mentioning in the ridge regression discussion, so you can find a relationship between this constant and this c, right? It's also a function of the range of your objective function, but you can always find. So essentially they are equivalent ways of writing the optimization problem, except that you have to, I mean, this constant and this c will not be the same, there will be different values. Okay. So this constraint is gone, this is no longer present here, right, that went into the objective function. Okay. So putting all of this back in and doing some algebra. You are going to be surprised at the algebra outcome of this. Anyone has already solved it? Know what it is? Looks familiar, right? Right, so it's essentially the same dual you will get, but your constraints are different. Yeah, I mean, this is already there, so it's just added for completeness sake. But what is important here is earlier while I had only a non-negativity constraint on alphas, now I have a upper bound on the value of alpha. So why is that? Because alpha is only c minus mu, right? Since alpha is c minus mu, so there has to be a upper bound on alpha. Okay, that's good. So what about the other KKT conditions? Yeah. So 1 to 7 are the KKT conditions. Okay. Right. So what do you notice here again? Well, you notice again that your beta is determined by your alpha I, yi, xi, just like you had earlier, right? Your beta is given by those xi's for which alphas will be non-zero, right? So like we had earlier, those xi's for which alpha is non-zero are called support points, okay, or support vectors, depending on how we want to look at it. Okay. Now let's go look at when it will be non-zero. Right, so when will alpha be 0? The whole thing is non-zero. When will this whole thing be non-zero? Right. When it lies at a large enough distance on the right side of the margin, right? What about xi? Xi will be 0. Somewhere here, xi's will be 0, right? So when xi's are 0, so you will be left with this term alone, right? Minus 1. That's just exactly the same condition that we had earlier, right? So if this is far enough away from the margin, then this will be non-zero, so alphas have to be 0. So we know for sure now, okay, the same thing, right, things that are on the right side of the margin, right means correct side, okay, things that are on the correct side of the margin, then alphas will be 0, so they won't contribute anything, right. So now what about things that are on the margin? Right. Is there a third case? We have to consider third case now, right? Right, we have to consider the third case, and which case what will happen? When xi will start increasing, right? When xi will become non-zero. Okay, if xi is non-zero, what does it imply? Okay, because my alpha is c minus mu I. Right, so if my xi is non-zero, then my mu i's will become 0, therefore my alpha i's will become c, right. So now how will this term go to 0? By suitably making xi large enough, right. So I will make xi large enough so that this term will go to 0, right, because this will be negative, right, or this will be less than 1. Right, so I will make this, I will adjust xi so that this term in the square bracket goes to 0, because my alpha I will be c. What's that?
In the second case,
Yeah.
that eta I is at 0.
This is because I don't want to penalize this case, right? This case also xi will be 0. Right, so this case xi is 0. This case also xi will be 0, right, because what I really need is, where is my condition, greater than or equal to 1 minus xi. So if it is equal to 1, so I can set xi to 0, correct. So in both these cases xi is 0. Okay. So does that make sense? Everyone with me here? So what are all the support vectors? Everything on the margin, everything on the wrong side of the margin as well, right. So everything for which alpha is non-zero will now become support vectors. So at the end of the day I am going to say that you are just going to use a package to solve all of these things, right. But it is like saying, yeah, anyway you are going to use Microsoft Windows, or I mean Mac OS X or something, why do you learn operating systems, right? So you need to know what the internals are, right? It's not the fact that you just use the tools that matters, right? When you're going to just use the tools, well, yeah, we can do a tool course, right? How to use the tools, right? How will you start up libSVM? It's not trivial, right? So many people I know actually run experiments with SVMs by just using the default parameter settings that the package will give. right? And don't laugh, I mean, there might be some of you in that. Okay, but then it's, you need to understand what is it that you are tuning, right? So now I told you about the C parameter, right? So you understand, you have some idea of what a large C means versus what a small c means, right? Instead of blindly saying that, okay, I am going to tune C from some number to some other number, right? So having an appreciation of what these things are doing actually helps you even use the tools better, right? So that's the whole idea behind doing all of this. It's not that I am going to expect you to come and derive a large margin classifier tomorrow. I mean, ideally